Jai Hind all, myself RP Singh, Assistant Professor, Department of Electronics and Communication Engineering, AKGEC Ghaziabad. Today I am going to discuss about BJT operation and characteristics. So before going to BJT, I would like to give some introduction about its counterpart, that is known as FET, field effect transistors. Because basic operation of BJT is amplification. Amplification means to raise the strength of the signal. So in communication system where we are communicating from long distance, we require amplification. Because of noise and some disturbances, signal will be weaker after traveling some distance. So we need amplifiers which is used in repeaters. BJT and FET both are used to amplify the signal. So before going to discuss about BJT, I would like to give some comparison between FET and BJT. Bipolar junction transistor, that is the full name of BJT, it is used to amplify the signal, and it amplifies the signal that is low AC. It cannot be used to amplify high powered AC signals. So as compared to FET, BJT is known as bipolar junction transistor. When it is properly biased, then current, that is output current, collector current, can be increased or decreased by applying input voltage between emitter and base terminal. And BJT is basically a device which uses both kind of carriers, electrons and holes, for its operation. But FET is a majority carrier device, and FET only one kind of carrier is used for the purpose of amplification and for the flow of current. So FET is a unipolar device and BJT is the bipolar device. In BJT, the current is controlled, output current is controlled via control at the input. So it's a current controlled voltage device, and BJT is voltage controlled voltage device. So this is a short comparison between BJT and FET. So now we are going to discuss about BJT, that is bipolar junction transistor. This is third terminal device, and it is very useful to amplify the signals, as well as it is also used in the switching application. We use BJT in digital logic and memory circuits. The basic principles involved, it is use of voltage between two terminals to control the current flowing in the third terminal. So now coming to the structure of BJT, this is the simplified structure of BJT. There is two PN junction diodes, NP, PN. So in this structure, as we can see, we have a N-type semiconductor, that is known as emitter. We will discuss about why it is called as emitter. We will discuss it later. And P-type base region and N-type collector region. So the first N-type semiconductor is emitter, it's a base, it's a collector. So it's NPN. Similarly, we can make PNP BJT. In PNP BJT, emitter is P-type, base is N-type, and collector is N-type. Why it is known as emitter or collector or base? It can be very clear after the operation of BJT. This junction, that is emitter base junction, is in short known as EB junction, emitter base junction. This is the first junction between NP, and this junction is known as collector base junction. So this is CB junction, this is EB junction. There are two junctions in BJT exist, EBG and CBG, in short it is called as. There are three modes of operation in BJT. In first mode, that is known as cutoff mode, emitter base junction and collector base junction, both are reverse biased. In saturation region, or we call it saturation mode operation, the emitter base junction and collector base junction, both the junctions will be in forward bias condition. If emitter base junction is forward biased and collector base junction is reverse biased, then this is the active mode of operation. In active mode of operation, BJT can be used as a amplifier. When we are going to use BJT as an amplifier, then we will use it in active mode. When BJT is in cutoff mode, then there will be no current and it looks like off switch. When BJT in forward bias condition, then we are getting excessive current and BJT can be considered as on switch. So if we are going to use BJT as an amplifier, then it put into active mode, and for another application, that is if you are going to use BJT as a switch, then we use cutoff and saturation mode. Now come to the basic operation of BJT. In the diagram we have taken BJT in active mode. In active mode, the emitter base junction, this is emitter and this is base. Emitter base junction is forward biased by connecting positive terminal to the base and negative terminal to the emitter. And in this mode, collector base junction is reverse biased by the connection which is shown in the diagram. So if we have forward biased this emitter base junction, this is basically PN junction diode. You can visualize this junction as PN junction diode. If PN junction diode is forward biased, then majority carriers will be injected into the base. Here the majority carrier is electron. So if in the emitter region we have majority electrons for the NPN transistor, then electrons will be injected to the base. And then if this electron have sufficient lifetime, sufficient diffusion length, then this electron will reach at the collector and collected at the collector terminal. So because of flow of this electron, we have collected some electrons which is injected from the emitter. So if we are at the collector end and we see to the emitter, then this n-type doped region will be visualized as a emitter. So from emitter, electrons will be injected into the base and at the collector end it will be collected. So here we can see the majority electrons will flow from N to P, from emitter to base. So this is the flow of current, this is the flow of electron, and obviously the direction of current flow will be reverse to flow of electron. At the collector terminal, we are getting electrons from emitter to collector. So direction of flow of electron is in this direction, in the forward direction, and we are getting collector current to the reverse direction of flow of electrons. So the current at the collector terminal can be controlled by the VBE, that is the base to emitter voltage. Also we can say that the value of collector current, the value of IC depends upon the injected electrons from the emitter to base. So if we want to increase IC in this mode, if we want to increase IC, in fact we wish to have maximum number of carriers collected. For example, if we have injected 10k electrons, 10k electrons have been injected from emitter to base, then we wish to have all the injected electrons will be collected at the collector terminal. Means IC will be exactly equal to IE. This is the ideal condition. In this situation, the output and the emitter current will be equal to IC. 100% efficiency. Number of electrons injected will reach at the collector. So ideally, we should have IC is equal to IE. To meet this efficiency, we require to make BJT with the following two constants. First thing is that we should make BJT in which there will be less number of recombinations. The number of electrons injected in this P region will be recombined with the holes. If there are 10k electrons injected into the base, and we have only 5 holes in the base, then only 5 electrons will be recombined. So electrons will be lost due to the recombination in the base. So we have to we need very less number of holes in the p type base region. To meet this requirement, we have to make BJT such that doping of emitter region should be much higher than doping of base region. This is the first requirement. Doping of emitter should be much higher than doping of base, so that we have very less number of holes in base region and we have maximum number of electrons in the emitter. So less recombination will take place. So loss of electrons due to recombination will be make much less by this adjustment. Now second thing is that we need that electrons will be injected at the base, will be collected at the collector terminal. So if width of the base is WB, then any electron which is injected from emitter have to cover this distance WB. So the second requirement, when we are going to design BJT, we should have diffusion length of electrons, means diffusion length of injected carriers should be much higher than this effective width of the base. So these are two basic criteria when we are going to design BJT and we wish to use the BJT for the purpose of amplification. So the forward bias on the emitter base junction will cause a current flow, and this current flow will depend upon the number of carriers collected at the emitter terminal. What will be the current value? What will be the current? So this IC will depend on the collected electrons, upon the number of electrons injected. So if more number of electrons will be injected, since doping of base is less, then more number of collected electrons obtained at the collector terminal. So IC will directly depend upon the value of VB. So this is shown in the equation that the collector current IC depends upon VB. In fact, this is PN junction diode. This is PN junction diode. You can visualize this as PN junction diode. And in PN junction diode, we know that the diode current can be written as, if we write diode current, then ID is equal to some saturation current. You may write I naught or IS, anything. That it's a saturation current, current due to thermally generated carriers. It is equal to e to the power V upon Vt minus 1. If I naught is very less, then ID is equal to I naught e to the power V upon Vt if I naught is less than 1, if it is very less. And in fact, it will be very less because of arrangements which is already discussed in the BJT. So IC will, so if we are going to write for the BJT, for the collector base terminal, then we can write IC as IS, that is the reverse saturation current at collector base terminal. IS is reverse saturation current at the collector base terminal. So IC is equal to IS e to the power VB, that is the forward bias voltage applied at emitter base junction. VB means IC is proportional to e to the power VB. IC depends on base to emitter voltage. It is very interesting, and this is known as common base configuration because base is common between emitter and basis and collector. So this is known as common base configuration. If we draw the circuit diagram, then for the common base configuration, circuit diagram can be drawn as, this is NPN, it's a P, it's a N, it's a P. This is collector, this is emitter, and this is base. So emitter base junction is forward biased. I am just drawing the circuit, and positive terminal connected to base and negative is connected to the emitter. So positive terminal is connected to base, negative is connected to emitter. So base is common between collector and base is common between emitter and collector both. So we have applied forward voltage between emitter and base, and reverse bias voltage between base to collector. So base to collector junction will be reverse biased by connecting collector terminal to the positive terminal of the battery, and base will be connected to the negative terminal of the battery. So base is now connected with negative terminal of the battery. So it's a common base configuration of BJT. It's a common base configuration. If base is common between emitter and collector, then it is known as common base configuration. If emitter is common between collector and base, then it is known as common emitter configuration. This is common base configuration. For this configuration, we get the conclusion that IC directly depends upon VB. There is no dependence on VCB. Ideally IC is independent from VCB. Whatever the value of VCB, IC doesn't vary. IC will be varied only with the variation in VB. It's a important result. If we wish to draw the plot between IC and VB in the active mode, we are going to the plot, draw the characteristic curve between IC and VB, where VB is the input voltage and IC is the output current. In fact, VB is the input and IC is the output. Then we get like this. Such kind of curve will be found. This is current will be varied only with VB, and it is independent from VC. Sorry, it's a VC. Sorry, there is some. This is VC. This is VCE. So IS is independent of VCE, and if we draw the value of current, the dependence of IC with VB, that is IC is taken at vertical axis and VB is taken at the horizontal axis, then we will have the curve very similar to junction diode. That is, current will be 0 before a particular voltage. If BJT is made from silicon, then this value will be 0.5 volt. So this is the characteristic curve in common base configuration. So it's a very important result we have obtained. And about the collector current directly composed of two components. First one is, that is the carriers which is emitted from the emitter and will be collected at the IC. So this is the description about the collector current, that is IC is equal to IS e to the power VB upon VT. So now make some observation about the base current. What about the base current? Before yes, we are going to discuss about base current. So if we consider the previous diagram which was drawn at the first phase, this is NPN transistor, NPN, this is emitter, this is base, and this is collector. And in active mode, if this junction is forward biased by this arrangement, collector, that is N type, this is forward biased. This is the voltage VBE, this is the voltage VCB. If we have applied some AC voltage also, then total voltage can be written as VB. This is the applied between emitter and base, and here the total voltage is VCB applied between collector and base. So this is the arrangement we have shown in the previous diagram. So now we are going to discuss about the base current. Now come to the point. Electrons will be injected into the base, and then it will be collected at the collector. Out of these carriers, out of these electrons, few electrons, this is the flow of electron, this is the flow of electron, few electrons will be recombined with the holes which is already available in the base. So holes will be recombined with these electrons, and then few of holes will be supplied from the battery. So in IB there are two current components. First one is IB1. This is due to the recombination. Recombining holes will be recombined with the injected electrons, and the loss of holes will be supplied by the battery. So first component is this, and the second component is this base current will be, even though this p type base is less doped, very lightly doped. There are very few number of carriers available in this base region, but carriers are available, and the majority carriers are holes. So if this junction, NP junction, is forward biased, then definitely few holes will be injected from base to emitter. This can be seen from the diagram. So these are the injected electrons from emitter to base. If it's shown, then shown by this diagram, and few of electrons will be recombining with holes available in this base region. Because of this, we have getting the current IB2, and few of holes which is available in this base region will be injected into the emitter. Because of this, we are also getting some current, some base current. So this is the second component of base current, that is IB2. What will be the direction of base current? It is in the direction of flow of holes. So the direction of base current will be inward. This is the direction of base current. This will be direction of collector current. No. If it is NPN, then direction will be change. So collector current direction will be inward, because electrons are coming in this direction, current will be in this direction. This is IC, and IE is in the direction of IE, and IC have in this are in same direction, and IB is in inward direction. So direction of the currents are shown in the diagram. This is the direction of IE, this is the IC, this is the IB. Why this IB is inward? Because holes are supplied from the battery, and the direction of flow of hole in this direction. So current will be obtained in the direction of holes. So we are getting two components of the IB current, IB1 and IB2, and IB is equal to IC upon beta. Beta is a constant factor, it's a device parameter, and beta depends upon the doping of base relative to emitter, as well as beta depends upon the region of the base width region, WB, the actual width of base region. So beta is responsible for the value of base current. We wish to have very less value of base current, because we do not need recombination of electrons in the base region to. So from this equation, it is evident that the value of IB depends upon beta. If beta is higher, then value of IB will be lower. So we should have beta is as high as possible. So now, to increase beta, to maximize efficiency, we should have already discussed WB should be less than the diffusion length of the injected carriers. In NPN, WB less than Ln. And the doping of emitter, that is doping of emitter, should be much higher than doping of base region. For with these two arrangements, beta can be maximized up to 200. If beta is 200, then the BJT can be used as a good amplifier. To obtain high beta, it is already written, which is highly desirable, means it represents gain. The base should be thin, that is WB small as possible, condition 1, and lightly doped, and the emitter heavily doped. The base should be lightly doped, emitter should be heavily doped. So IB depend upon beta. IB is equal to, value of IC is equal to IS e to the power VB upon VT. So this is the equation for base current. Equation number 2. Equation number 1 is IC is equal to IS e to the power VB by VT. This is the equation number 1. So now make some concentration at the emitter current. Emitter current directly depends upon the number of electrons injected from emitter into the base region. Maximum portion of emitter current will be obtained by the number of electrons which is injected from emitter to base, and the second portion of emitter current will be obtained from the holes which is injected from base to emitter. So if we are going to write this the value of emitter current, then it will be composed of IB and IC. I is equal to IC plus IB if we apply KCL at this node. So I am again writing, again drawing the diagram to apply KCL. This is the emitter, this is the base, this is the collector. It's a P, it's a N, it's a P, it's a N, NPN transistor, and emitter base junction is forward biased and collector base junction is reverse biased. Okay, so electrons will be injected from emitter to base and it will be collected at the collector. So the direction of IC will be inward and direction of IE will be like this, and this is the direction of IB. So if we apply the KCL at this terminal, at this node, then we get IE is equal to IC plus IE, that is outgoing current will be exactly equal to incoming current. IE is equal to IC plus IB. This is the value of emitter current, and we have already derived some expression in equation 2, that is IB is equal to IS upon beta e to the power VB upon VT. So putting the value of IB, in this equation, we get the equation 4 like this: IE is equal to IC. What is the value of IC? I am writing it for erasing. If we put the value of IC in this equation and IB, also IB, IE will be equal to value of IC IS e to the power VB upon VT plus value of IB IS upon beta VB by VT plus IS upon beta e to the power VB. IE is equal to IS e to the power VB upon beta plus IS upon beta VB upon VT. VB upon VT. So IE will be equal to, if we have taken common this term, this quantity, then 1 plus 1 upon beta IS e to the power VB by VT. So equation 4 is obtained, that is I is equal to beta plus 1 upon beta, beta plus 1 upon beta IS e to the power VB upon VT. This is basically IC. So I is equal to beta plus 1 upon beta, this equation number 5. And also we know that IC is equal to alpha I. From where it is obtained? IC depends upon number of electrons injected from the emitter. Basically this is emitter current. So IC depends upon emitter current. How much emitter current, how much electrons injected will decide the IC. So IC will be equal to alpha IE. So by equation number 6 and equation number 5, we have alpha is equal to beta plus 1 upon alpha is equal to beta plus 1 upon beta. We have just written I is equal to beta plus 1 upon beta is equal to I to the power VB upon VT, and I is equal to alpha I. By comparing equation number 5 and equation number 6, we are getting the value of alpha. Alpha is equal to beta upon beta plus 1, and I is equal to IS upon alpha e to the power VB upon beta, e to the power VB upon VT. So now beta can be expressed as alpha upon 1 minus alpha. In fact, equation number 9 and equation number 7 both are same. Both are same equations. Okay. And alpha is known as common emitter gain. Either alpha is also known as current transfer ratio. It decides how much current have been transferred. So from this equation we get alpha is equal to IC upon IE. It decides number of emitter current which is transferred at the collector. Number of electrons which is injected from emitter will be collected at the collector end. So it is known as current transfer ratio. It is known as current transfer ratio. Also it is known as common base current gain. So it is known as also known as common base current gain, either known as current transfer ratio. And the value of alpha, what should be the value of alpha? We require IC is equal to IE ideally, which is already written here. Ideally we should have IC is equal to IE. To have IC is equal to IE, alpha should be 1. So we need to maximize the value of alpha, and for the ideal diode, beta should be greater than 100, that is 200 or more, and we need alpha should be 1. Okay, and alpha is called as common base current gain, and beta is known as common emitter current gain. Beta is known as common emitter current gain. So this is the relationship between beta and alpha. Beta should be high and alpha should be unity. Ideally, if alpha is 1, then IC will be IE, and this is the requirement. 100% efficiency. Number of electrons will be injected, all will be collected if alpha is 1. So ideally we should have alpha equal to 1, that is but practically we should have alpha 0.99 to 0.98. So this is the basic of NPN transistor, and this is the basic structure. This is the simplified structure of BJT bipole junction transistor. So practically the device is not symmetrical, and the emitter and collector cannot be interchanged. So this is the structure of BJT. So we will discuss the other topics in coming lectures. So thanks for today's lecture. Thanks to all.